I'm Bill Masson, and going to tell you about surveys by Unmanned Aerial System, or UAS, also known as UAVs, Unmanned Aerial Vehicles, better known by everybody as drones, but that's not politically correct right now, so we'll call it UAS for our purposes. This is the real star of the show, the SensiFly eBee. That's the equipment that we use. A little closer look at it. It's got a wingspan of about 38 inches. Nominal mission takeoff weight is about 1.5 pounds. Nominal endurance is 50 minutes, although that can be affected by environmental conditions like temperature and wind. Cruises at 22 to 28 knots and maximum speed of 49 knots. So how does it work? It uses some sophisticated automation software and a telemetry system that is two-way, that sends flight data to a laptop, and the laptop sends control inputs and information up to the airplane. It's got a high resolution onboard camera and a GPS, and all of those things together it uses to produce stereo ortho photos. So after it gets the photos, the positioning data and the photos are imported into a post-flight processing program that does the photogrammetric calculations and uses pixel matching technology to stitch the photos together and make a point cloud of discrete color identified data points. And that resulting point cloud can be made into a digital terrain model, and that can be exported to CAD or whatever software that you might be using for mapping or measurement or modeling purposes. So let's take a look at it. This is a typical takeoff. It does a series of onboard checks and lets you know when it's ready for launch. I've watched that at least 100 times and I still hold my breath. This is the control system on the laptop on the ground. You can see it's the airplane's following its pre-programmed flight paths, but those flight paths can be edited and changed at any point real time. You can delete waypoints, add waypoints, move waypoints. Also provide commands for flight maneuvers. That's the telemetry, the flight data, the airspeed, altitude, attitude, and heading, and battery conditions and whatnot. This is a map showing the ortho photo, the ortho mosaic that was generated from the photos. All of those red dots indicate a location where the photo was taken. This site here, what we're looking at, is about 76 acres, and this is case study number 1, which we're about to look into. So this was a gravel pit flown to determine a volume of a pile. We just wanted the volume for one pile, the client did, but we decided since we were out there we'd just fly the whole quarry, since it only took 35 minutes to fly the whole thing. It was actually planned for a mission of about 38 minutes, but the wind came up and depleted battery faster than we had anticipated. It was fine. We already had collected all of the data that we were after, so it didn't really bother us that much. So 76 acres, 35 minutes, 320 photos. Processing time for the computer is about 8 hours. And note that this flight, it was 35 minutes long, generated 48,333,432 3D data points. That's astonishing to me, for that much data to be collected in so short a time. So the results to me are nothing short of phenomenal. Now keep in mind, what we're flying over is not a photograph. This is a point cloud with colorized data points, individual data points, 48 million plus of them. All of this data was collected in 35 minutes of flight time. That's the pile in question that we were after right there. And so as a bonus, we have volumes for all the other piles that are there too if we need them. And it turns out the client later on asked us to provide volumes for those piles. They had some use for them, and so we were happy to do it. With one survey, we collected all of that data. These tanks are actually rusted. That's missing data since we had to truncate that flight time. But once again, we weren't too concerned about that. The other thing to notice here, or to think about, is this was 76 acres that was surveyed, topoed fairly well, in incredible detail, and we didn't have to walk any part of that except for where we set our targets out. That was all topoed without putting a footprint on the ground. That's something to think about for environmentally sensitive areas or dangerous areas or places where you don't want to put people. So here's the pile in question. You can see the detail that's provided with this survey. That's about 500,000 data points that represent that pile. That's a considerable amount of detail, I think you'd agree. And just to kind of restate the obvious, you know, using 10,000 or tens of thousands or hundreds of thousands of data points for your calculations compared to the few hundred that you probably would have collected with traditional GPS RTK methods translates into a quantum leap in volume measurement accuracy. Not to mention, well, I'm sure probably orders of magnitude, many orders of magnitude better accuracy. Not to mention the time factor. It would have taken hours to topo that with GPS, as opposed to something less than 30 minutes to take care of it with this method. So this is case study 2. It's a landfill for a small town in Wyoming. We wanted to record baseline conditions in photographs. We weren't concerned about the topography so much, but we used a fairly abbreviated flight plan because we were just considering photography, but the topography ended up coming out very nicely too. So this was 73 acres, 12 minutes, 6 seconds flight time. We still generated somewhere north of 22 million data points. This is the landfill as it appears in Google Earth. And this is the ortho mosaic that we generated from our flight, overlaid into Google Earth. That's straight out of the software. There wasn't any manipulation or rubber sheeting or anything to fit it into Google Earth, and you can see it matches perfectly. This was the flight plan that we used for that. You can see it's much less dense than the other ones that you may have seen here earlier. That's because we were just concerned about the photos. We weren't after detailed topography, but I think you'll agree that the results were pretty impressive anyway. Once again, keep in mind that this is a point cloud that we're looking at here. When we get closer to the ground here, in a few seconds, you'll be able to see the individual data points, and it makes it a little more clear what's going on here. But yeah, this isn't a photo, this is just data. And a huge amount of data to be captured in 12 minutes is just it's a phenomenal event. So here's an example of the resolution. I'll zoom in a little bit here, and I think you'll agree that's much better than any satellite imagery that's available, at least commercially available, that I've seen. You can see a palette off to the lower right there, and you can almost make out the printing on the red bag there towards the center. So this is our last case study. It's a topographic survey for an area where road realignment was going to take place. It was a county road that they had some issues with some bridges, and they determined that it was more cost effective to realign the road than it was to do the repairs on the bridges. So we mapped 76 acres. Actual flight time was 26 minutes 30 seconds, 269 photos. Computer processing time again was about 8 hours, and we generated somewhere north of 42 million data points. Now you'll notice at certain points here this looks translucent. That's because you're looking through the point cloud. It's those are data points on the surface. They're not. I can't emphasize that enough. It's data that we're flying over. The nice thing about this is the amount of data that's captured in so short amount of time. You can you bring back data from the field that, and there's things that you never imagined that you needed, that you might want to use. You know, this information could be used for watershed analysis. It could be used for existing conditions. It could be used for asset management, condition indexing. You know, the sky's the limit, and it's all collected at one time, so you don't have to go back out to the field and determine, you know, for instance, on the highway there, you can measure the striping intervals if you wanted to, because it's captured there. This is these are contours that I generated in AutoCAD and Civil 3D from the point cloud that we just looked at. Those are 2-foot contour intervals, and you can see off to the to the right of center there, that's the proposed center line of the new alignment for the county road there. And we flew this about 2 weeks after the flight that you just looked at. It had snowed, and we went out and reflew it to determine how repeatable was the data and how did the snow affect our data. And if you look closely at the contour lines, those are the contour lines that were generated after it snowed. The snow was anywhere from 1/10 to 3/10 of a foot deep, and you can see that those contour lines are somewhere around 1/10 to 3/10 offset, just like you'd expect. And what this told me was that this is extremely reliable data, and it's very reproducible, and it gave me a great deal of confidence in the data that we were getting out of this. That's all I had to present, and I just wanted to thank you and for letting us share our excitement with you. I am very excited about this. I feel very fortunate and honored and blessed to be working with this equipment and doing what I'm doing right now, and we would love to have you be a part of that. I think it's a revolutionary technology, and we can do some amazing things with it, I think. So thank you for your time.